All right. So let's look at now JAL. The only difference is that instead of using a base register, we are using PC here. Okay. And other thing you can note that is that, you know, offset is here, it's between 1 and 20. The offset here is smaller. Okay, we are not going to those details because that you have understood already. The two things we are doing, that return address we are saving to register RD, and then increasing PC to by offset, but it's a PC relative jump. So we'll look at the current value. So this is JL instruction, and then we are jumping to a location which is related to this PC. Okay. Now you will understand when you will study linker and loader, you will understand how JL and JLR are actually utilized. Okay. Only thing you need to remember now is a PC relative jump. So we are jumping to a location which is related to current instruction that we are executing, which is JAL. Okay. So now let's start. Take the value of PC. Okay. And we are here. Let's assume that this is a clock cycle. We are somewhere here. It means that PC value has been updated from previous cycle. So this value is current. So PC value goes to these two places. Now PC plus 4 is available here. Almost at the same time as instruction is available here. Okay. Now instruction of course goes to different places, right? So we are here. Okay. Now tell me one thing. I mean, I'm asking, say, are we reading or writing into register in this instruction?
No, sir. Sir, in RD we will
Yeah,
write.
sure. So that's right. We are not reading anything, but we are writing in PC plus 4, we are writing into RD. So this part will be used. Remaining two, although reading may happen here, but we will not use that, right? The only thing we are using here is this part. Okay. Okay, so instruction goes 7 to 31 bits comes here, and then we are generating offset or total immediate. Okay, and that value goes here. Okay, now what are we going to add this to? PC, right? So PC plus this immediate value will go to PC. So now PC, it means that the PC is here. The current value of PC we are taking. Okay, so this control signal, which is A cell, should be, this one should be 1 or 1. So, this PC value will come here. Similarly, this offset value has to go here. So this control signal should also be 1. So it means that A cell should be 1 and B cell should also be 1. Okay. Now output is available here. Now you apply add signal here. So output is available here. What is this output now? Is the PC plus offset. Okay. Now this goes where? So this multiplexer, and if you select 1 or branch taken, which is nothing but 1, then input is available here. Okay, this completes the first part. Second part is that PC plus 4 must be saved into return address or register RD or RA. I mean, here in this case, we are considering this RD. RD address is given, or which register it is given by these bits. The first part was clear, right? First part was that we have taken the value of PC, read the instruction, it goes here, immediate field, we sign extend this, create 31-bit number, it comes here, you select 1, the B cell is equal to 1, so this is selected. Now this should be added to value of PC, right? So this value of PC is taken. It goes here. This control signal is 1, so it comes to ALU. Now at the output of ALU, we have PC plus this immediate field, right? Which is sign extent. Okay, all right. So this is available. Where should this go to? This should go to PC. Now, if you select branch taken, now who will decide on this branch taken or not? Uh, when instruction is comes here, right? And this control logic sees that is JAL. It means that branch is taken. So it will select the upper input, and value is available here at the input of PC. Now, second part is that we will have to say PC plus 4 into register. So this value at the same time when we are fetching this previous thing that we have done, the value comes here, PC plus 4 is calculated. Now this goes here, okay. And then we have to select 2, W cell is equal to 2, which is PC plus 4. The value comes here and goes to the register block, the register file. Now register file at the right port, this value is available. And when you set the value of RD, now value of RD is comes directly from the instruction. At the next clock edge, okay, let's assume that we start from here. The next clock edge, this value is PC plus 4 is updated into corresponding register. Similarly, PC plus immediate, which is available here, will go to PC. The PC value will change. All right, is it clear? Any question? Now next to our upper immediate is LUI and AUI PC. These are very straightforward instructions, right? So there is nothing. So we take 20-bit field from here, and then what is LUI? LUI is to a register this field 20 bits. Okay, so these two 20 bits which are given in the instruction and loaded into the upper side of, so register is of 32 bits. The upper 20 bits will be this one. Okay, all right. So it's very simple. Okay, so LUIRD is equal to this. Okay, so what are we going to do? So we are going to take the PC values here, take instruction, look at the offset, and of course RD value will come from here because we are using RD. Okay, these are 20 bits. Okay, it comes here. This multiplexer, set this to 1, so the value goes here. Okay, and then you set it to B, so this value comes out here. So take the value of PC. Instruction is read. RD value goes here. RD, okay, and then immediate field, which is it's available here. Your B select is 1, so this is selected, goes to LU. Okay, and now this value we are putting into register RD, and we are not adding anything. So ALU will just not perform anything, and then this value will be available at output. Okay, so the value goes here. Okay, and then this value is available at this multiplexer. Okay, because output of this multiplexer is going to register 5. Okay, and then we are going to select 1, so control signal 1, so this will be selected. So it means that now this 20-bit offset time extended is available here, and this address of the register is given at this one, first the address port, and then corresponding register will be written at the next clock edge. And at the same time, you do PC is equal to PC plus 4. So both values will get updated at the next clock cycle, right? Essentially at this point in time. Okay, is it okay? Yes or no?
Yes, sir.
Okay, all right. So this something that's shown in blue is what we have traced it earlier. Okay, similarly AUIPC we can do. Okay, now instead of taking 12-bit and saving into register RD, what we are doing is that we are also taking the current value of PC and adding to this 20 bits that we are getting from here. Upper 20 bits we are taking and then putting remaining as 0. So basically here we are taking the value of PC and then this addition will be performed here and finally the value will, from this route the value will go to PC. So let me just show that. Okay, just a minute. Okay, so this AUIPC, so it will be something like this. This block shows PC is equal to PC plus 4. Instruction is taking in, destination register address will come from here. So we'll take 12 bits here and then okay, and then we create from this immediate field of 31 bits. Okay, and then input will go here, output will finally go to register file using this stuff. And correspondingly multiplexer will be set. Okay, all right. So now notice the control signals that we are applying at each phase, right? So for example, register file, the control signal should be 1. That's a register write enable should be 1. Similarly, PC select will be PC plus 4 because we are not jumping. So when we jump, only upper input is used, right? And so on. Okay. So now with this one, we complete the design of complete data path. Okay. And you see that is so simple, right? It means that now for RS, as for RISC-V, 32-bit integer type of instruction set, we have completed. So it means that whatever data path we have designed will execute all these instructions that we see here. Of course, some we are not covered, right? Like call, etc. Okay. So so for so we see that RV32I has just 47 instructions. Now I will, as an exercise, please read about Intel and see how many instructions it has. And then 37 instructions that we have studied so far are good enough to run any C program. That's a beauty. Right? Okay. So just want to recap about LUI and AUIPC. Okay, so when we say LUI, we are loading upper immediate 12 bits and remaining are extended with zeros. So I have used the word sign extension, it's not correct. So basically 12 bits of upper 12 bits of register will come from instruction. Oh, just a minute. Okay, upper 20 bits will come from instruction and bottom 20 bits will be zeros. Okay, 12 bits will be 0 and 20 will come from instruction. So it's not really sign extension, but extending 20 bits that are coming to 32 bits. Similarly, AUIPC. AIPC has similarly we are doing operation here. Okay, so now we have completed the design of RV31I. What should we do next? we will focus on this part. Okay, so we have completed this. Okay, what notice that we have used only single cycle design, that is in this time period complete instruction execution will be over, and each instruction is split into 5 phases, and not all instructions are active in all 5 phases, right? Okay, some instructions don't use write back into register, some instructions don't use memory. Instruction fetch is common, instruction code decode is common. Okay, some instructions don't have an execute phase, right? So we just write back something. All right. Say for example, last but one instruction. Okay, wherever we are not using ALU, okay, that it means that execution phase is not happening. All right. So now we move to control logic. Another few minutes. Let's discuss about control logic part, and then next class we'll start designing control logic. We have seen processor has two important parts. One is data path, which consists of ALU, registers, and program counter. Okay. Then control part, and it interfaces with memory, which is instruction memory and data memory. We have shown separately. Okay. Now we are focusing here the control part. Now the processor in general consists of register, data path, ALU, program counter, and control logic, right? So we'll focus on control logic, which is shown in orange. What do we need to do here? Now we see something that in red, orange color line is control signals, and we have to apply these control signals at appropriate time. It means that these values for each instruction, these values must have some value, which is either 0, 1, or combination of multiple bits. Okay, so let's quickly look at it. Now all these control signals or control bits we have already studied. Okay, even in the last class we have studied these. These are the one here. Okay, so you can read it from here. I have just repeated the same things. Let's look at only one control signal, which is PC select. The PC select is this one. Okay, this control signal for the multiplexer here. So now let's find out in what condition it should be enabled. And so far we have already studied it, right? Now PC cell has two values, right? Is 0 and 1. If you go back, you can see that there are two values, 0 and 1. Okay, 0 is when you give 0, it means that PC is equal to PC plus 4. This input will be taken in and set to PC. So this is the regular instruction. When you are executing one instruction after other, then you'll take that. For branches and jump, this control signal should be 1, such that the PC value will be ALU out. Now ALU out will be what? Okay, ALU out will be after addition of base address and offset or some other operation. Output will come to PC. Okay, so now we represent the diagram as follows. For regular instructions, PC cell should always be 0. Fine. Now let's look at all branch instructions. Okay, now I have sent you one green sheet. Okay, and then that sheet, if you open, you will find out that for each instruction corresponding opcode number, function 3 field, okay, and function 7 field. Now for all branch instruction, which is BEQ, BNE, BLT, BGE, BLTU, and BGEU, we see the opcode is this one. Okay, it means the opcode is the same for branch. Opcode field is same, which is equivalent to hexadecimal value of 63. Only functional 3 field changes. Okay, 0, 0, 1, and so on. So in general, if you look at 63, if you say that if instruction that you are fetching to control unit and opcode field corresponds to 63, we read this, it turns out to be this bit pattern, which is 63, then you know that BEQ is a branch kind of instruction, hence PC select should be 1. Okay, so for all branch instruction, etc., we have seen this input should be selected, right, which comes from ALU. All right, so so that logic, so in this way we can have the logic, right? Okay, so now we can create a circuit which is a combinational circuit, is a comparator. Okay, and into this we take the value of from the opcode, because opcode instruction is fetched and opcode value will be fed to this one, and it compares with 63. Okay, and if it's equivalent to 63, then corresponding PC select value should be set. Okay, okay, so if it is 63, it means the branch is to be taken. Okay, all right. It means that this value should be equal to 1. PC select should be 1. Okay, all right. So now let's look at, okay. So let's look at jump now. Again, we have to generate control signal for this one. Okay, and then look at the opcode for JALR and JAL. Opcode is different. Okay, then we'll have to generate different logic for these two, right? If it is the same, then things would have been easy. Like in case of BEQ, branch instruction, any branch instruction will have opcode field is equal to 63. Okay, when you compare the opcode field which is received the instruction matches with 63, right, then you know the branch is to be taken and corresponding control signal should be set to 1. Otherwise, if does not match, so 63 anyway is input. If this value does not match, it's greater than or smaller than, then they should be set to 0. So it's very simple. Here you have to create two such circuits, and one take the opcode value and compare with 6F, which correspond to JAL. If it matches, then it's a branch instruction, right? It means that control should be 1. Okay, that is as we have seen in this case, right? PC select should be 1. Similarly, if it's 67, then also PC select should be 1, otherwise 0. Now we can combine these two to create output, right? So you tell me which of the two is correct logic for jump instruction. So PC, if it is jump instruction, PC cell should be 1. Is it correct or this one is correct, bottom one? Yashi, please answer.
Yes, sir. So bottom one.
Bottom one, because either one of the, if either one is true, then we will sell, this will become so. Very good, thank you. So we have now seen 3 cases: regular instruction, branch instruction, and jump instruction, and we can combine these 3, right, in this way. So this is for branch instruction, and this is for JAL and JLR. Okay, right? Okay, 67, 67, right? All right. So now we can put them with OR gate. It means that if any one of these is true or 1, then output should be 1. It means that if output is 63 or 67, whether it is branch instruction or jump instruction, either of the jump instruction, then upper input or control signal should be 1, such that this is to be selected. This one is to be selected, upper input, which corresponds to ALU out. Okay, all right. Okay, so let's now stop here. And then from next class onwards, we'll repeat this again for each block that we have seen. And then finally, what we'll do is that we'll create a table like this for each instruction. For each instruction, there are 3 inputs. Instruction that comes to control logic, then BEQ, BLT that comes from comparator, and then we have to generate these outputs. For each one, we generate this output. And then we look at the values here, each value, and then create a logic, something like this. Okay, so we'll take this up in the next class. If you have any question, please send me an email about it. Please go through the PPT again because it's very important.